Welcome to Extreme Makeover NGSS Edition, High School Waves episode. And here our goal is to take the kind of classic tabletop experiment you might do in a high school physics class, looking at waves from the perspective of a string sitting there on your tabletop bench, and try and turn that into something that's much more contextualized in the real world, and really motivate our entire study of waves by looking at seismic waves. This vignette basically comes from the high school 3-course model, Physics of the Universe, and there's a section here on earthquake waves that starts off the whole sequence of studying waves in the electromagnetic spectrum. We're going to start off by looking at this view here. We're looking at a web camera view of a man at the Microsoft headquarters. And he's sitting there and he's eating his lunch, he's looking around. And what's going on? Alright, they're doing something you should never do. They're getting up and walking around during the earthquake, and oh my. What's interesting here is we want to answer the question, when does the man know that an earthquake has occurred? Let's start looking at this again. He's looking around. Why is he looking around? What was going on there? Listen. At this point, everybody in the room seems to know there's an earthquake. They've said the word earthquake. I don't know if you can hear that in the audio of the clip. And they all know that there's an earthquake before we notice any shaking here in the video. And then all of a sudden we see this very strong shaking. At this point, I like to have my students draw what they see. This is a way for them to describe the motion that they've observed. Sometimes they just draw pictures of these little monitors and they draw little shake marks on there. Sometimes they draw it in a graphical form. I give them a kind of a vague set of instructions of trying to represent the intensity of shaking that they saw and the motion that they saw. And then we can go ahead and move them over to watching this picture. This is the same video again, except now we've done what scientists like to do. We've taken more precise measurements from a nearby seismic recording station, and we've synced it with the video. And now this is not an exact sync here because this is a station that's not exactly at the same spot, so we're not going to be seeing the exact same motions, but it was a pretty good approximation of this actual earthquake in 2000 in the Microsoft headquarters. And you can start seeing that the ups and downs here represent the intensity of shaking that starts off kind of weak, gets really strong, and dies off again. And at this point, we now are ready to really introduce our main phenomena. And as teachers, I want to step back and look at that for a second. What is our phenomenon, our anchoring phenomenon for this lesson? Well, you might say, earthquakes. And I would argue that that's not really the greatest explanation of a phenomenon. That it's an event in the world that you can observe and explain. At the high school level, we want to be doing something more than just earthquakes. I think the phenomena that we're going to be trying to explain here is in the earthquake that we saw, that people felt kind of a weak pulse of shaking followed by a much stronger pulse of shaking. And we want to figure out why that is. To do that, we're going to look at a different earthquake, one that we can get more data from. And this particular earthquake has a special place in my heart because this earthquake occurred my very first day of being a high school earth science teacher. I had just finished teaching and closed my door and said, oh my goodness, what have I gotten myself into? And more importantly, what am I going to do tomorrow? And around that exact moment, with my head in my hands, an earthquake hit, and I felt it. And I was here in the San Francisco Bay Area, and so as a former research scientist that studied earthquakes, the first thing I did is I went online and grabbed all the data I could. And each one of these yellow circles here represents all sorts of different seismic recording stations all over the Bay Area. And I grabbed ones from the red stations here and looked at how each one of these different locations recorded the shaking from that single earthquake. Each one of those stations records a graph that looks like this. On the horizontal axis is time in seconds, and on the vertical axis is the shaking intensity. I like to ask my students, how long did this earthquake last? Well, it looks like, I don't know, a little bit more than 20 seconds. Kept on going there. I also like to ask them this shaking intensity. It has some positive values and some negative values. What exactly does that mean? Well, if we look at it more carefully, the shaking intensity is listed here in microns per second, which is a velocity. And what seismologists have done is they've come up with a convention that when you have things that are moving upwards, we call that a positive velocity, and downwards is a negative velocity. So we're going to be looking at shaking intensities that are both upwards and downwards. And what I want the students to do is to look at their shaking record here and try and find the place with the most intense, or the time with the most intense shaking. That's right here on my graph, and in this particular case, it's negative. It just means it's downward intense shaking. We don't really care about the direction when we're talking about the most intense. That's an absolute value question. So we want to read off the time and the magnitude or shaking intensity on the vertical axis. So at this point, I distribute seismograms, have students enter their data into an online spreadsheet. I'll show you that in a moment. And we're going to discuss some patterns of amplitude. So let's get started. Here are all of our students' data entered in with their time that the peak shaking occurs and the strongest shaking that was recorded. You can see some positive and negative numbers in there for each one of these stations. And on each one of the records, it shows the three-letter abbreviation that you saw on this picture here from those maps. So each one of those three-letter abbreviations is a different location. Now, if I ask my students, what patterns do you see in here? It's a little bit hard to tell. I mean, you might get some students that offer some interesting ideas about patterns that they see, but we always ask our students, well, what does a scientist do when they have a data table that looks like this? Well, they might say, graph it. And that's excellent thinking. But we are now going to be using a tool that Earth scientists like to use when they have a table of data. And Earth scientists don't just like to graph things, they also like to map things. And we're going to take these same data and show them on a map. In this map here, here's our San Francisco Bay Area outlined with the black coastline. And each one of these dots here represents one of those stations that we recorded, and the size of the dot represents the intensity of shaking at that spot. And you can see we have a grid of longitude and latitude on here. And I ask my students, where exactly is the earthquake source? What is the latitude and longitude of the earthquake source? And we have two different teams that have entered in their estimate into the online spreadsheet, and it showed up automatically here. Team 1 put the source of the shaking here, close to where the shaking is the most intense. Team 6, however, indicated that they thought the shaking was over here, and I asked them why, and they said, well, because there's a couple different stations around here that all kind of have big stuff, and over here there's little stuff, and they're starting to basically interpolate between there and say that somehow this source, there's probably, if we had data from right here, we'd see that it was much bigger than these surrounding areas, and that's how they're estimating this. And so we are basically using data to try to answer a question: where was the earthquake source? My students also like to know where the real earthquake source was. What's the answer? And of course, this is calculated automatically by computers using a much better technique than the one we're using here. But in terms of this task, I don't want to tell them the answer, because the answer is both 1 and 6 have reasonable arguments to support their claim. And they've got evidence to support their claim, reasoning. Therefore, each one of them is right, and the only way we'd be able to tell it apart is if we had more data. And this is how real science works. We don't get to look the answer up in the back of the book or go on Google. We're trying to figure out something new that nobody has ever discovered before, and we want to make sure our students start struggling with that right here, right now. One of the things you notice when you look at that graph, there's a spatial pattern. Let's go back to it. If we assumed that the earthquake source was going to be where the shaking was strongest, we noticed that shaking got weaker as you went further away. And this is a general pattern that we see, kind of like a bullseye centered around the earthquake source. And if that's true, why is it true? What's causing that? And that's the question that we're going to investigate now, or the phenomenon that we're going to investigate in a little bit more detail. I'd like to have my students start thinking about what these data look like when we graph them. That was another idea that we had, and in this particular case I'm going to show them a blank graph where the horizontal axis shows the arrival time of peak shaking, like we measured from the seismic recordings, and the vertical axis shows the strongest shaking. Now, we kind of have the general idea that we'll feel shaking a little bit later if we're further away from the earthquake source. So what is the case, what would the graph look like if we were to plot the arrival time versus peak shaking? Is it going to look like that, or like that, or like that? I have my students draw this in their science notebook, their sort of anticipation about what this might look like. And then we actually use the data from the spreadsheet that they entered in and take a look at it. And here it is. It is not a straight line, but there is a definite trend or pattern here, with the further away you get, the weaker the shaking. And what do we make of this interesting curve, though, where when you're really close, it's really strong shaking? Well, this pattern here should start looking familiar. This is what we see as an effect of geometric spreading. We saw this when we were looking at radiation. We saw it when we were looking at electrostatics and Coulomb's law, Newton's law of gravitation. All of these have a 1 over r squared term in them, and the same is true for seismic waves and for sound. This is late in our course that we were teaching this information about waves, so we've actually already seen this 1 over r squared term in Coulomb's law and Newton's law of gravitation much earlier in the course, and we're going to make that connection to our students so that they can apply all the reasoning that they had from that past experience to this experience. And we can actually check the graph to see if it matches a 1 over r squared. So now, here was our original phenomena. In the earthquake, the people felt a weak pulse of shaking followed by a much stronger pulse of shaking. Can we answer that yet? I don't think we can explain our phenomenon. We can start saying, well, if they were closer to the source or farther from the source, we've learned something about earthquakes and waves and how they move through the earth, but we haven't yet got enough information to answer this. So let's go ahead and see if we can figure out some more details by looking in more detail at our seismic recordings. I asked my students, does your seismogram have 2 clear pulses like the ones that I show here? Here's a green one and a red one right there. And the vast majority of students will raise their hand, showing that they indeed do see 2 clear pulses. There's a few that don't. The next question is, which pulse has a stronger shaking intensity? Is it the first pulse or the second pulse? And we raise our hands for the first pulse. Not in this one, and in fact, very few students are able to show us the first pulse is stronger. And then I say, how about the second pulse? And just about everybody in the class raises their hand, and we now have a pattern, an interesting thing that we need to explain. Why is it that the second pulse is stronger than the first pulse? We're going to move again to a different earthquake and look at a computer simulation. I'm going to hit play here, and this is a simulation of the 1906 earthquake. And this is shown in real time here. As I'm talking, this represents how quickly seismic waves were moving away from the earthquake source as we went along, if we were there in April 18th, 1906. And we watch this video, and there's just so much rich stuff going on in here. So many interesting things that you can notice as you're looking around in here. And our students see so many of them. They're noticing all sorts of things. We love to give them the opportunity to look at this video and ask questions, playing it over and over again and helping them come up with constructive questions about what they're seeing. What we see with these colors, first of all, is that these represent the intensity of shaking, with the blue colors representing weak shaking, and then red colors and yellow colors representing stronger shaking. But if you look at this, you can see there's kind of an abrupt line here between the bluish stuff and the yellowish stuff. And what is that exactly? Remember the 2 pulses of shaking that we saw in our seismic recordings? They're here. And what I'm noticing, though, about these is if I look at the first pulse of shaking must hit when I first feel this purple low-intensity wave hitting me. And the second pulse of shaking is going to be when this yellow higher-intensity wave hits me. And does that match what we saw? Yes, it does. We saw that second pulse of shaking was stronger. But the other thing that's really interesting is that the distance between the blue pulse and the yellow pulse seems to be getting a lot bigger. Here we are at the end of the movie at 22 seconds, or actually not even near the end, but here we are at 22 seconds, and look how much space there is between the blue and the yellow. But if you back up towards the beginning, the blue and the yellow are actually really close in here. So somehow one of them is running away from the other, escaping the other. And this leads us to an interesting kinesthetic demo that we can do. Before we see that kinesthetic example, I wanted to point out that this video has a companion website from the USGS that shows you step by step what's going on there. So it gives you a little bit of narration so that if you're looking at this for the first time, you can feel a little bit more comfortable when you're in front of your students. Now, the kinesthetic activity, I usually get 2 students to come up to volunteer, one representing my hare and another one a tortoise to do a race. And my hare, I always take 2 steps for every 1 step that my slow-moving tortoise takes. And I start the race, and they start off at the starting line at the exact same moment, but the hare starts moving farther and farther ahead. Just like that blue pulse of energy seemed to be moving farther and farther ahead. And the longer you let this race go on, the longer the time between when the tortoise arrives and when the hare arrives at the finish line. And this is exactly what we were seeing with our seismic waves. We know that one of those seismic waves must be moving faster than the other. This allows us to start making a graphical organizer to represent these 2 pulses of shaking that we observed both in the video at Microsoft, that we saw in our seismic recordings, that we saw in the 1906 earthquake simulation, and that we now have a little bit better understanding. There seems to be one wave that arrives first and one that arrives second. The one that arrives first must be getting there first because it's moving faster. And in fact, we can look at that simulation and measure that that's moving about 6 kilometers per second, while our second arriving wave is moving slower at about 3 kilometers a second. We also know that the second pulse that we feel is stronger than the first pulse, which is weaker. And you notice that we're starting to set up some nice alliteration. We have some strong, some slow, some second. That leads us to calling this one here an S wave. And we'll come up with a name for that other one a little bit later. We have a question though. How is it that some waves might travel faster than others? And to answer that, I like to give a kinesthetic model that helps our students see this. I use a human conga line where each person represents a piece of Earth's crust, and their arms between them represent springs that are connecting between them. Now, you may not think of rock as very springy, but in fact, actually, when you are pushing hard enough, like plates do when they move plate tectonics, rocks actually can compress a lot like a spring does and bounce back just like a spring does. So if you imagine we have a very rigid spring and I start to add an earthquake pulse in here, I push against one side, what's going to happen is that that spring is very rigid and the rest of this side is going to pop over very quickly. A strong spring means a quick energy transfer. But let's look at what happens when we have some softer material. Now, when I push over on this side here of my human conga line, and I ask my students, instead of holding their arms rigid, to have kind of floppy arms when I push. So what happens is, as I push, I've taken some compression of my student's arm, and now, instead of having it instantly cause the whole right side to pop over, what we see is that it takes time, because the people have to move before they compress their springs enough to push on the other side, and that slows down the energy transfer. If earthquake waves travel faster through more rigid material, we can say something about the rigidity of our 2 pulses that we saw. Our first one that arrives fast must be going through more rigid material, and the slower pulse must be going through softer material. But now we have a problem. It seems like we have these 2 different pulses that are moving through different materials, but that's not true. Those 2 pulses have to move through the same material. They both start at the earthquake source, and they both end up at the seismic recording station. So how can it be that they're moving at different speeds? It looks like they're moving through different materials. Well, this tells us that there must be different types of waves that move through the material differently. At this point, I'd like to show a slinky, where you can use that to demonstrate different ways that you can excite the slinky, with either compressional waves, where you push and pull, or shear waves, where you're shaking the slinky from side to side. But which pulse is which? How do we label our two pulses between these compressional and shear waves? To answer that question, we need to understand a little bit more about materials. And I'm going to show you a balloon held between my hands, and that will help us understand some things about material properties. When I have that balloon between my hands, I can push my two hands together so that I'm pushing against the balloon, and I feel it resist my motion. However, I can also move my hands a different way. I can move one hand up and the other hand down. And this is a motion that we call shear motion. And when I do that, the balloon kind of just twists around freely in between my hands. It doesn't resist my motion. And that is because air, the material filling the balloon, is very weak in shear, but strong in compression. And in fact, this is true of most materials. Most materials are stronger in shear than they are in compression. Now we know from a few moments ago that a stronger material causes a faster wave. So our faster waves must be associated with compression, and our slower waves must be associated with a shear wave. So let's fill in our table. Our material that was more rigid has to be moving through the earth with a push or pull or a compressional wave, and our material that was softer must be moving with a shear wave because those move slower. And now we actually have a name for our P waves because of the compression or pushes and pull. And we also like to say that they are primary waves because they arrive first, another word for first being primary. At this point, our students should be able to put in their science notebook an explanation about why we feel two pulses of shaking. They should be able to put all these pieces together. Now, it's pretty complicated. They might need to use their graphic organizer. Their explanation might include the idea that there's two types of waves, that materials are more rigid in compression than they are in shear. Add that to the fact that waves move faster through rigid materials, and that faster moving waves arrive first. And you put all those things together, and we feel the faster moving compressional pulse first, and the slower shear pulse second. This might be our overall claim, and there's some reasoning in here. And what's the evidence? Well, we can point to each piece of evidence that we built along the way. The balloon evidence for the material strength, the conga line for the rigid materials and wave speed, and the tortoise and the hare for faster moving waves arriving first. This is a complete scientific explanation that our students can start constructing by themselves in their notebooks. But can we explain our original phenomenon? In the earthquake, people felt a weak pulse of shaking followed by a much stronger second pulse of shaking. Well, this is pretty good. We've got two pulses of shaking explained, but what we don't have explained is the complete phenomenon with the weak pulse being first and the stronger pulse going second. So what's up with that? Well, to understand this, we need to give our students some more information. And I usually use my hands to demonstrate that there are three main types of faults. When we have our hands together and I put them there, and one of my hands on top goes upwards, I call that a thrust fault. If I take them and put them and cuss them together and have the hand on top go downwards, that's called a normal fault. And then there's a strike-slip fault, where I put my hands side by side and I move them past one another. Now, when you think about these motions with my hands, how does that relate to our balloon demo, where we were looking at the difference between compression and shear? In each case, I'm moving my hands past each other in a shearing motion. In fact, earthquakes are primarily shear events. They release more energy as shear excitations than they do in compression. With just that single piece of information about the way plates are sliding past one another, our students now should be able to explain why our second S-wave pulse is stronger. And their explanation might include things like plates move past one another in a sudden shearing lurch, which means that earthquakes release more energy as shear than as compression, which means that earthquake waves that transmit shearing excitations have higher amplitude than compression. And those waves that move by shearing excitations, we call those our S waves. I think we can finally explain our phenomenon. However, we haven't learned everything we can about waves. In fact, we've just scratched the surface. And we're going to use this opportunity to transition now to looking at some other aspects of waves using those same earthquake recordings that we had before. When you look at those seismic recordings in more detail, I've taken one of the ones, the exact same one I showed you earlier in this presentation, but I stretched it out a little bit so you could see a little bit more detail. And do you see any pattern that you might notice in the shape of these wiggles here? And now you can look at all the different seismic recordings in our library of seismic recordings and see, is that pattern consistent? And you might notice that we now have the opportunity to introduce the word frequency here. The first pulse seems to have a higher frequency than the second pulse. We can now add yet another column to our graphic organizer that helps us keep everything straight between these P and S waves, and that is that the waves that arrive first, those P waves, they have a higher frequency than the S waves. And now you can see from this that we've now introduced some really important words related to waves. We have amplitude, we have frequency, there's the traveling speed of the wave, but one of the things we haven't got in here is the wavelength. Now, we haven't been able to see the wavelength in any of our seismic recordings because these all measure in time on the horizontal axis. And if you're looking for a wavelength, you need to have a distance on that horizontal axis. What we can do is we can actually look at a different data set from, unfortunately, yet another earthquake. Now, in this particular case, we're going to be looking near the town of Long Beach here, and an oil company installed thousands of seismic recording devices that are going to allow us to see an earthquake. And we're going to look at a very small one, this Carson earthquake, which is a magnitude 2.5, and we're going to look in this blue area here, which I have zoomed in on the next page. The blue area has on the left side of it is the 710 freeway. Going down the middle here is the 405 freeway, one of the world's busiest freeways, and the Queen Mary is down here if anybody's ever gone down to Long Beach on a tourist event. And this is the general geographic area, but I'm going to show you now the data. Here we have along the left side the 710 freeway and going across the 405 freeway, and these reds and blues represent up and down motion here. And now I ask you, have you had an earthquake yet? There's lots of ups and downs, but take a look at where they are, and I'm going to go ahead and continue along here, and let's see if we can figure it out. Ah, there's the earthquake. Let's go ahead and go back here and look. All this stuff that's happening in the first few seconds as I scrub along here, that's not an earthquake. Those ups and downs that you're seeing are the tiny vibrations from cars driving across the freeway, bouncing up and down, exciting the earth, and we can actually see that in this data set, which is really remarkable. And as we move along, eventually we know that an earthquake has occurred because we can see it. And now, at this point, let's go back here. At this point here, you can see that these faint colors represent weak shaking. So if you're looking in this area over here, what are you seeing? Are you seeing the P wave or the S wave? And now where does the strong S wave begin? That's right about over here, and you can see that it starts moving across, and all of a sudden we're seeing all S wave energy. And then as we continue to watch it, the waves are moving, bouncing around off of different basins in the area, and you're getting interference patterns, and slowly but surely you're seeing the waves die out. But what we've got is we have very clear evidence for an earthquake, and now you can start seeing the earthquake's wavelength. That's the distance between trough to trough, or crest to crest, and I put on here a 1 kilometer grid cell for you so you can get a sense of that. And let's take a look on the next slide. We'll take in more detail at the difference in wavelength between the P waves and S waves in this earthquake. Here's a snapshot where we can just barely see those P waves in there, and here's a snapshot where we have S waves. Now let's go ahead and take a little bit of a bite from this here and move it there, and this one here, we'll move it over there, and we put them side by side, and what do you notice? You notice crest, 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 and crest, crest, crest. In a 4 kilometer section of P wave, you got 4 crests, almost exactly, and in a 4 kilometer section of S waves, you have 4 crests, almost exactly in this picture. It looks like they have really similar wavelengths. Now that's really, I think, kind of amazing and surprising because they have such different speeds, such different frequencies, yet they have the same wavelength in here. So let's summarize. We have different frequencies, same wavelength, and different speeds, with the P having a higher frequency and the P having a higher speed. With those 3 things there, can you come up with some sort of a relationship between these 3 different variables, frequency, wavelength, and speed? Here are 3 options for you. Let's use V for velocity instead of speed. Lambda can be our wavelength, and F can be our frequency. And here are 3 possible equations that could relate those. Which ones of these are possible? Well, you know that when you have a faster V for P wave, you also have a higher frequency. So this one seems to work, but so does this one. This one here in the middle definitely doesn't work because as the frequency goes up, the speed goes down with F in the denominator there. So we're starting to see, we're asking our students not just to calculate things using a formula, but actually come up with the formula from empirical evidence. And at this point, we can't quite distinguish between 2 of our options, so we need more data. At this point, I'll send my students over to one of these PhET simulators. I don't know if you've ever played with them, but they're pretty amazing. And you can adjust the frequency, adjust the amplitude, and get out a ruler here and look at wavelengths. Go ahead and get a stopwatch in there and figure out how quickly things move through here. And in this particular case, you can see our waves are traveling in both cases at 320 meters per second. A 500 hertz wave has a wavelength of 0.64 meters, and our 300 hertz wave has a wavelength of 1.06 meters. We can actually plug these into different equations and come up with which one is the accurate equation that represents the relationship between frequency, wavelength, and velocity. While we were doing all of that, I didn't start off with this as teachers for you or as students, but let's see what we did. This is the performance expectation that we've been trying to teach to this entire lesson. HSPS 4-1. Use mathematical representations to support a claim regarding relationships among frequency, wavelength, and the speed of waves traveling in various media. And it mentions here seismic waves in the clarification statement, and assessment is limited to algebraic relationships and describing those relationships qualitatively, meaning what we were just doing, where one of them goes up, the other should go down. We actually had our students come up with this equation. And this is what this NGSS performance expectation is asking us to do. It's not asking us to use the equation, but we need to support a claim about the relationship. And whenever you support a claim, you need evidence. And our evidence came from our observation of earthquake waves, and also later our observations of sound waves. This is a pretty remarkable thing to be able to do, to have our students coming up with their own equations to represent things. And I think they're going to have a lot more buy-in in that process than if we had started off on day 1 showing them the correct equation and having them plug in numbers to it. Now, the high school 3-course model also goes further than this and asks us to integrate some Earth and space science performance expectations into each of our high school courses. And in this particular case, we can relate what we've been doing to 2 performance expectations. One of them here is develop a model based on evidence of Earth's interior to describe the cycling of matter by thermal convection. Well, we didn't get anything into thermal convection just yet, but we did start looking at the layers of the Earth and how we know about the layers of the Earth. Because remember, this is asking a model based on evidence. So what's the evidence that there are different layers inside the Earth? And that's where we're going to try and extend this a little bit further with our students. We might give them a summative assessment where they're trying to imagine a scenario where there's an earthquake here, and here we're looking at a slice through the Earth with different materials, and ask them things about these different houses here, A, B, and C. We're going to ask them, which layer will the seismic waves travel the fastest in? The hard granite or the sandstone? We'd like to ask them to draw a model illustrating how the waves travel from the earthquake source to each house, being sure to depict the wavelength, the amplitude, or the frequency, and how those change as the waves move from one layer to the next. I'll show you an example of what student work might look like for that. We can ask them which house might feel the shaking first. We can ask them which house might feel the shaking at the strongest frequency or the wavelengths, and we can ask them to plug in some actual numbers into their equations to tell us how quickly things are moving or what wavelengths we might actually expect. Here are two examples of student models. You can have models of wavelength represented by little waves like this, or as waves emanating outwards like we saw in the sound wave simulator in the PhET simulator. And we can start asking the question, these are pretty neat models showing how the wavelength changes as the waves travel from one medium to the next. What's not well depicted in here is the amplitude. Take a look how the amplitude doesn't seem to change as you get further away from the earthquake source in either of these models. So that would be a way that we could improve both of these models even further. After our students worked on that challenging summative assessment as groups, we're going to then ask them to individually create a poster helping communicate how seismic waves help us figure out what's inside the Earth. Your poster should be able to support or refute the claim that the Earth has different layers with different velocities. And they'll be drawing upon the ideas that they demonstrated here in the group activity and all the evidence that they collected along the way. And so finally now we have some evidence of what's going on inside Earth's interior. Now that our students have mastered some of the basics of waves introduced by seismic waves, including amplitude, frequency, wavelength, and gotten the idea that waves travel at a certain speed, they propagate through materials, we can start looking at another type of wave, which is where the course would pick up from here, looking at the electromagnetic spectrum and moving on from there. That's the way that I would do an extreme makeover to my high school unit teaching waves, starting with seismic waves, as we did in this example.